Today we're going to see some applications of what we've been doing with solving equations that involve logarithms and exponents. It's called exponential and logarithmic models. So first thing I want to talk about is exponential growth. And we've graphed this exponential growth function, and what we saw with it was just how fast that it grew as it went up the scale right here. And so in this case, time is going to be my axis down here. So as time goes on, the idea with exponential growth model is that it grows faster and faster and faster. How fast does it grow? Well, it depends on some variables. For instance, this k right here. This k is known as my growth. I'm going to call it growth factor. Okay. It tells me how fast it's growing. T, this represents time. So time, it could be in years, it could be in hours, it could be in minutes, it could be any number of things. And this a sub 0 right here is the amount that I have present at time equals 0. Or in other words, it's my initial, I'm going to call it the initial amount. Initial number of people, initial number of bacteria, whatever we're talking about, that is growing exponentially. And so f of t is the amount I have after t hours or t minutes, whatever time t is. Amount after, maybe I should throw the word time in here. The amount after time t that I would have. Now you might be thinking, this looks kind of familiar. Well, it should. This is the same as my continuously compounded interest problem, where I had the amount that I had in my account equals PE $t. R was my rate, same as my growth factor. T was in time, P was my principal, the initial amount of money I put in, and so forth. So if you wanted to use PERT on this still, you could, and you would get every answer correct. I'm going to try to use this new notation that we have up here. So like I said, we're going to do some real world problems here. We're going to start with zombies. That's obviously real world. Okay. So 25 zombies come into a city, and each zombie is going to convert 2 more people into a zombie each day. I don't know how, I'm not really caught up on all my Walking Dead talk. However they convert, I don't know if they bite them or look at them weird or however that works. But they're going to convert them. So I want to write the population of zombies as a function of time. In the second part of this, I want to know how many zombies I'm going to have after 2 weeks. So let's start with our equation. It's a function of time, A naught E to the KT. Let's plug in what we know. We know that we're starting off with 25 zombies coming into our city. This E right here is just Euler's E. I don't know if I mentioned that or not. And I don't know the growth factor. The growth factor is not 2 or 3 or whatever you're thinking it is. The growth factor, I need to find out what it is. But what I do know, it tells me this information right here converts 2 more people. So it means I'm going to have 1 zombie going to convert into 2 more is going to come out. So I'm going to have a total of 3 by day 1. So that means after 1 day, put that 1 day in for time, I'm going to have 3 times as many zombies if every zombie converts 2 more people each day. So it's tripling every day. So I'll just triple my initial amount and put it over here. Now what I want to do is I want to solve this for k. So I'm going to divide both sides by 25. This gives me 3 equals e. K times 1 is just k. I'm going to convert this to a logarithmic expression. So the e comes over. It's going to go underneath the log on this side. Well, that just gives me natural log. That's 3. That is my k. I want you to be careful with this. Go ahead and decimal this out, but I want you to keep more decimals than you normally would. On this one, let's just say keep 5 decimal places. 1.09. I got 861 on that. You can definitely double check me. I just took the natural log of 3. So now I'm ready to write this as a function of time. So my 25 zombies are going to grow by, it looks like about 9.8% each day, almost 10%. And then throw the T on there. So to answer the second half of this question, if I'm wondering how many zombies I'm going to have after 14 days, all I need to do is plug in 14 And after I plugged 14 in for T, oh man, these zombies blew up in 2 weeks. So 119,570,394 would be what it would be rounded to the nearest person. Like I said, two answers on this. I'm going to put this one, and I'm going to put this whole equation. So make sure you get those two boxed in so I can find them. Okay, let's look at the other side of this, exponential decay. Exponential decay is just going to be where a given substance or people or amount or whatever, I guess it would have been people in the last problem, people that are not zombies are just, as time goes on, you see my time is my x-axis down here. As time goes on, they get smaller and smaller and smaller until they get right next to zero. Okay. A lot of my stuff is the same on this. The one difference that we're going to have on this is that this k right here is going to be negative this time. And I'm going to make it so that automatically comes out for you. You don't have to worry with it. K will come out to be negative. But if you're working a decay function, k is negative. If you're working a problem like we just did, k came out to be positive because it was growth. So I just made up an element here. I call it dexterium is what I call it, dexterium. And so it has a half-life of 7,539 years. In case you don't know what half-life is the amount of time required it takes for any given substance to decay by 1/2. So after 7,539 years, if however much dexterium I have, it's decayed, it's rotted out, whatever happens to it, by half. Okay. So what I want to do is, this time I'm just looking for a function of time on this. Okay. I can plug in numbers if I want to. We might go over that towards the end of the problem. But I'm just looking for a function of time. So luckily, I'm using the same formula, E to KT. And I'm given a starting amount. I don't have to have a starting amount, but in this problem, they did give me a starting amount. It says the researcher starts with 40 grams. E to the K. I don't know what K is. K is going to be the beef of the problem of what you have to work out. So that's what I'm working down towards. But I need to find T and F of T. And they didn't give me, the only other number that they gave me was 7,539. And I'm pretty sure I need to plug that in up here for my T. Well, according to what I know about half-life now, this 40 grams after 7,539 years is going to reduce down to just 20 grams. I'm just going to solve the same way I did for K on the last one. So I'm going to start off by dividing both sides by 40. So that's going to give me just 1/2 over here. E to the, rearrange those numbers. The coefficient makes me feel better when you arrange that way. Right, the E still comes over. You're going to have a lot of natural log in your homework. 7,539 K. So if I divide both sides by 7,539, it's going to tell me what K is equal to. Now, this is obviously decaying very slowly. This is taking 7,539 years to get down to 20 grams. My decay rate is going to be small. So do me a favor on this. Don't just put down a really small number on it, or don't just put down a bunch of zeros. Actually put down some numbers that are significant. So even to 4 decimal places, I have 0, 0, 0, 0. Okay. I'm going to go ahead and put down 5 numbers that actually mean something right here. 5 significant figures. 9, 1, 9, 4, 2 is what I got. Like I said, that's the meat of the problem. Plug this K back in right here with your initial amount, and we get our final answer. Switch color so it stands out a little bit. So as a function of time, if I start with 40 grams, it is going to decay. And notice it came out to be negative because it's going down. Like I said, it was automatically going to come out for us. And this would be my answer. If I'm wondering how much I'll have left maybe after 1,000 years, what I could do is I could definitely plug in 1,000 right there for T and solve that out. Okay. All right, one more type of problem I want to talk about. It's called logistic growth. A logistic growth model, I'm not going to have you derive this at all, okay, but it looks something like this. And the idea with a logistic growth is that the model grows kind of at a logarithmic pace until it reaches something called the carrying capacity, and it levels off. And that carrying capacity works as a horizontal asymptote that it cannot get past. And so one example of this is if you've ever seen the TV show on Netflix, Lost. Now, I'm going to warn you, this is one of those shows, the more that you watch it, the madder that you get, just because they, I don't know, it just kept on getting weirder and weirder. The idea is that there's some people on this island, and there's only so many resources on this island for people to have. And so after a while, the people just, instead of just keeping on growing and growing, they kind of level off after a while. A better example of this is I think of Dexter High School, and I like to ask my classes, how many people do you think we can fit in Dexter High School? Not really how many people you fit, but how many students can we have in here? You know, keeping in mind that we don't like to go over, what, about 30 per class. We only have so many lockers. We have so many classrooms. We only have so many teachers. What would actually be the carrying capacity where we just would not be able to hold any more students? I know right now we're running just under 600, but you know, can we get up to 700 people or 800 people? Well, whatever that max is right there, you could actually work your way up to it all the way until you just could not get past a certain number anymore. And that's what happens a lot with universities. We're about to do a problem that has to do with University of Central Florida. One other thing I want to talk about on this is the carrying capacity. Whatever this number C is, that is the carrying capacity. Notice that is the only number that's in my numerator. So it's a really easy number to pick off. The rest of the variables in this, I'm not going to worry too much about. I'm just going to plug it in as to where they make sense. Okay. So we have the University of Central Florida. I think these are the guys that are doing so great in football. They haven't lost a game in like 2.5 seasons or something. I don't know. Anyway, they are this. In 2008, they were the 6th largest university in the country, and so the number of students can be modeled by this function over here, where t is in time, t is time in years, and t equals 0 corresponds to 1970. We talked about that a couple weeks ago. So, how many students attended UCF in 2000? Okay, so to find out what this is, well, first of all, in 2000, that's going to be t equals 30. Okay? If t equals 30, then what I want to do is I want to plug 30 in for this t into my function. I'm going to let you guys go ahead and plug in 30 right here. Pause the video and see if your answer matches up to mine. Be really careful with your calculator and putting everything into parentheses that you need. So go ahead and pause. Yeah, to the nearest student, I got 43,990 students. So that means sometime between 1970 and the year 2000, we had to pass this 40,000 mark that we were looking for. So let's see how we can get to that 40,000 mark. So if I plug in 40,000, now I'm wanting to plug this actually in for my f of x this time. I'm going to work it down here at the bottom. I get 40,000 equals 50,000 over 1 plus 5e to the negative 1.2 t. And I have the unfortunate task now of solving this for this t right here. Look where that t is. It's hidden in the denominator inside an exponential function up on top. Wow, that's going to be tough to get to. Now, if you've had me for a while, you've probably heard my story on moving the hat. I can definitely move the hat on this one and take 50,000 divided by 40,000 and simply get 5/4. And that makes it so the problem looks, oh, so much better. Trouble writing the number 5 suddenly. Here we go, 5e to the negative 1.2t. Okay. If you haven't heard my story on moving the hat, what I did in this step was I actually took the reciprocal of both sides and then multiplied by 50,000. And that will get you to the same spot. If you haven't heard my story on moving the hat, come talk to me and we'll get you keyed. Next up, I'm going to subtract 1 from both sides. I get 1/4 equals 5e to the negative 1.2t. And remember my goal on this, when we talked about solving these types of equations, the only thing I want on one side of the equal sign is a base raised to a power. So in this case, the only thing I'm wanting on this side of the equal sign is e raised to a power. So I need to divide both sides by 5. Okay, now I'm going to convert it to a logarithmic equation. So I'm solving for t the same way I've solved for k now in the previous problems. So I get a natural log of 1/20 equals negative 0.12t. And notice I haven't typed anything in my calculator yet. Negative 0.12. I didn't do this t. So I'm just left with t on this right side, and I finally get the number of years that it took. It took right at 25 years to get this. So does that answer the question? When did the population reach? 25 years after 1970. So it would be the year of 1995. You guys think I'm old right now, but actually in 1995, I didn't even have my license yet. I'm still in middle school. Anyway, part C down here, find the carrying capacity. Save the easiest part for the end. Whatever's on top right here, 50,000. So whatever is stopping this from growing past 50,000, whether it's professors, whether it's the size of the campus, whether it's dorm room space, whatever it is, I can expect this number to get closer and closer and closer to 50,000 based off what they had in 2008, but it's never going to surpass it.